Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of the Argand diagram or complex plane, and this was a particularly useful way of representing complex numbers on this two-dimensional plane. And we came up with this idea of the two-dimensional plane by realizing that we could think of the imaginary unit in a multiplicative way as transforming the real number line by rotating it by 90 degrees. And similarly, we also saw that we could think of the imaginary unit as acting on the imaginary number line in a multiplicative way by rotating that by 90 degrees. So that was this rather abstract idea of the imaginary unit that we invented as kind of solutions to polynomial equations turned out to have a particularly nice geometric interpretation as simply rotating the number line by 90 degrees when we think of it acting in this multiplicative way. And similarly, we also asked ourselves the question, or we studied how the imaginary unit, or in turn the imaginary numbers, all the imaginary numbers on the imaginary number line, act on the real number line in an additive way. So recall when we talked about the real number line, we could think of the real numbers as acting on themselves in an additive way by shifting the number line left and right. And we saw that by acting the imaginary numbers on the real number line in an additive way, shifted it now up and down, because we have this now additional dimension that we can think about in which the imaginary numbers extend into. And by some symmetric properties, we could also think of how the real number line acted on the imaginary number line in an additive way. That was to say that if we had an imaginary number and it was acted on by a real number, it shifted it either at right or left, depending on the sign of the real number. And towards the end of that video, we also showed how we could write a complex number not in this only in this form of kind of x plus iy, but in what was known as the polar form. And that described a complex number in terms of the angle that it was away from the positive real part of the complex plane, or the positive real axis, and its distance away from the origin, which we call the modulus. And this angle we refer to as the argument. So what I want to do now is I want to start from where we left off there and look at some examples of how to translate some of the complex numbers that we know in this what is called Cartesian form, this x plus iy form, and see if we can write them in our polar form just using some simple trigonometry. So let's go to our example. So our first example we've got here, I've described, here's my complex plane, and I'm going to take the point here which is going to be in other words, 1 plus I, right? Because I can see that that's 1 unit shifted to the right and 1 unit shifted upwards. So in other words, I think of this as 1 plus I. And I can also write kind of this vector here coming from the origin, where the base of this vector is at my origin of my complex plane and the tip is at that point there. And what I want to do is I want to find the length of that vector. Well, the length is given by the modulus, and that is in other words written as the square root of 1 plus 1, because obviously the width of this vector is 1 because I go 1 unit along, and it's also 1 unit high, and just using Pythagoras' theorem, that gives us that the length of this is in other words the square root of 2. Now if I project this thing down to the x-axis and I want to fill out here an angle, we can see that the angle here is just simply given by the arc tangent, or the tan inverse of 1, right? In other words here, because we've got that this angle that I've got starting from the positive real part of the complex plane going upwards, I've got that the height of this triangle is 1 and the width of it is 1, so that tells me if I do kind of tan of opposite over adjacent, that's arctan of 1, which in other words is pi over 4. So that tells us that this angle here is pi over 4, and that completely describes our complex number here, z equals 1 plus I, in polar form, right? Its argument here is pi over 4 because that's the angle that it's got from the positive real part of the axis. And we measure that in a positively because it's going in an anti-clockwise direction. So recall we measure the argument positive if we're going in an anti-clockwise direction from the positive real axis, and we measure it negatively if we're going in the clockwise direction, which we'll see in just a moment. So given that data, we can simply write z in the following way. We can write it as the square root of 2 cosine of pi over 4 plus I sine pi over 4. Right? And that's just simply just using some simple trigonometry here. And splitting up these things into right angle triangles. So let's look at a slightly kind of more awkward example where again we're going to write this complex number in polar form, but this time we're going to take it in a kind of a different quadrant. So we're going to take it in this bottom left quadrant. So down here, this thing actually is describing the complex number -1 minus the square root of 3i. The reason I've picked this one is because it gives us a nice triangle in which we know some standard angles for. So again, we can draw our arrow emanating from the origin of our complex plane. And the first task is to find the length of this arrow. So the length of this arrow is just going to be given by the modulus. And the modulus is given by simply the square root of the 1 term squared plus the square root of 3 terms squared, which in other words is the square root of 1 plus 3, which is the square root of 4, which in other words is 2. So we can fill that in. Here we have that the modulus of z is equal to 2. Now, again, projecting this over now, but this time to the y-axis, we can see that this coordinate here is actually this minus the square root of 3i. In other words, it's got a height of the minus the square root of 3. And we want to find out what this angle is first. And we're going to label this angle here as theta. So how would we find this angle theta? And this is just a simple trigonometric problem. We can use arctangent again to solve it. So the angle theta is simply going to be given by arctangent of 1 over the square root of 3, which is known to be pi over 6. And we can see that by just looking at our right angle triangle here. The opposite, the kind of width of our triangle is of width 1, and its height is of root 3. So you just get that it's opposite over adjacent. In other words, arctan of 1 over root 3. But is that now our argument? Is the argument of our complex number? In this situation, it is not, right? Because that is not the angle that we're measuring from the positive part of the real axis. So in other words, we need to add on a term here. So let's fill that in of pi over 6. We need to add on this angle here, which is pi over 2. Right? In other words, it's 90 degrees. But not only do we need to do that, recall that we're moving now in the clockwise direction. And when we move in the clockwise direction, we measure our argument as negative. When we move in the anti-clockwise direction, we measure it as positive. In the clockwise direction, we measure it as negative. So in other words, we do pi over 2 plus pi over 6, which gives us our total angle away from the positive real axis. And then we make it negative because we're moving in the clockwise direction. So that simply gives us that the argument here is minus 2 pi over 3. So that means we can write our complex number here as 2 times by cosine 2 pi over 3 minus I sine 2 pi over 3. And that's just using this property that you can take if you have a negative angle inside a sine function, you can take that negative sign outside the front of the sine. And because cosine is an even function, cosine of minus theta is the same as cosine of theta. So that minus sign is not needed. So that's some examples there of how to write complex numbers from its Cartesian form into polar form. And very much, I think the approach to do this is to kind of draw a picture, see which kind of quadrant your complex number lies in, and then just adding up kind of multiples of pi over 2 of 90 degrees to make sure that you get the right angle for the argument, and recalling that the argument is the angle measured from the positive part of the real axis. We measure it in this way that it's positive if we're going in an anti-clockwise direction and negative if we're going in a clockwise direction. But the next thing we want to look at now is, well, we talked before about how to do complex addition on our, at least the real part of the axis, or the real axis and the imaginary axis. So we saw that how we could act imaginary numbers on the real axis by shifting it up and down, and we saw how we could act real numbers on the imaginary axis by shifting them right and left. But the next question is to say, well, how can I think about complex addition on the entire plane? How can I take so say, for example, I take a singular point here. So I've got a particular example of, say, z equals 1 plus 2i. How can I think of this thing acting on the entire plane in a reasonable way, in an additive way? So how does it transform the plane, the complex plane, in an additive way? Well, let's start with some of the stuff that we know. So how would z equals 1 plus 2i act on the number 0 in an additive way? Well, what that would do is it would transform it along to the right by 1 unit, because that's our kind of number 1 coming from the real part of z. And then it would transform it upwards by 2 units, which is coming from the fact that we have this component 2i, and we think of plus 2i as shifting upwards by 2. Okay, but we can restore this thing, and we can also think of it in a kind of maybe more convenient way, is let's draw now an arrow coming from our origin up to this point as z equals 1 plus 2i, which we're representing in this way of 1 plus 2i, which is reasonable because we're thinking of addition as these shifting actions. In other words, it's a shift 1 to the right and 2 upwards. And we can otherwise think of kind of this additive action of z on 0 as simply taking the point 0 and moving it along that arrow, so moving it along the kind of base of that arrow to the tip of the arrow, and that gives us exactly the same thing as what we did before, as kind of moving along by 1 unit and moving upwards by 2 units. So that's how we can say, that's how Z here acts on 0 in an additive way. So much like how we talked about the real number line acting on itself in an additive way by shifting it right and left, we think of this one number here, Z, acting on the number 0 as shifting it from 0 to this point Z. That is, it shifts it 1 unit along and 2 units upwards. But what about some other points? We know we can maybe look at some other points now on the real axis. How do we think it would act on the number 4, say? Well, on the number 4 it does, we've already kind of seen this. It would again do exactly what it did to 0. It shifts it along by 1 unit and then shifts it from this point upwards by 2 units. So that's where we would end up. That's, in other words, it's saying what the action of Z is on 4 in an additive way. How would Z transform the number 4 in an additive way? So if I do Z plus 4, how would it transform it? Now, another way of doing it, which is going to be kind of more useful, is let's take this red vector that we've got and transport it along without changing it, but now bringing the base of that arrow to where this green dot is, in other words, where the number 4 is. So now we've moved it along, we've not transformed it in any way, or we've not kind of stretched it or shifted it. All we've done is kind of transport it along, so its base now is at the point 4. Now if we just move that green dot along that kind of arrow, so from its base to its tip, then that's exactly what we got before as thinking about the action of Z on the number 4 in an additive way. That's how Z transformed the number 4 in an additive way. And we can realize that we can build this for kind of all sorts of numbers. Now, if we take the number -6, we can take the red arrow, take its base along to -6, and then we ask ourselves the question, how does Z transform the number -6 in an additive way? It just shifts it along that arrow along to its tip. So that's, in other words, it would take the number -6 to this new number here, which is represented where this new green dot is. And similarly, we can extend this as well over to the imaginary axis. We've already seen how to do this. So again, we've got the number here -2i. We transport the red arrow down, so its tip, so its base now is at where the green dot is, and then we move the green dot along this arrow, so it's now at its tip, and that's what it would transform the number -2i to, right? In other words, it's saying that if we have Z is 1 plus 2i, and it acts on -2i in an additive way, it transforms it to the number 1. And that kind of makes sense, right? We've got 1 plus 2i plus -2i equals 1. That's what we've shown. Well, so we've seen, and we've kind of already talked about before, how complex numbers might act on the imaginary axis by themselves and the real axis by themselves. But what about now if I just take a general complex number? Well, it would make sense that whatever it did to the real numbers and the imaginary numbers, that it should do the same to a general complex number. Let's construct a definition of addition, in other words, how Z acts on W in an additive way, as it acts in the same way as it does to all the other numbers. So how would Z now act on W in an additive way? What it would do, how would it transform W? I can take my red arrow, I can transport it along to W, so now that the base of that arrow is at the point W, and then I take the point W and I kind of shift it along the arrow, so now it's at the tip of the arrow, and that, in other words, is now representing the point Z plus W. So that's kind of us thinking about how Z, this complex number 1 plus 2i, is acting on W in an additive way. But we can break this down into its individual components. That's going to be useful, and it's going to allow us to construct our general definition of complex addition. So looking, let's say, at just the first part of Z here, the real part of Z, how would that act on the number 0 in an additive way? Well, we've already seen in the kind of just looking at real numbers, that would shift it along by 1 unit. Okay, so that makes sense. Now let's take the number, the real part of W, in other words, the number 3. How would that act on the number 1 now in an additive way? Well, that would shift it along by 3 units. In other words, it takes it along to 4. Okay, very good. Now let's start looking at the imaginary parts of Z. So if we look at the imaginary part of Z, this 2i, that would now do what? If that acts on the number 4, we've already seen that that would shift it upwards by 2 units. Okay, and then finally, the last thing to do is to look at the imaginary part of W, and we see that if that acts on the number now 4 plus 2i, we see that that would now shift it upwards again by 1 unit. In other words, we've seen that doing this kind of combination of breaking it up into the kind of real part actions and the imaginary actions, we just do shifting to the right and then shifting upwards, was the same as what we saw just a minute ago by kind of transporting that vector along and then moving the point along that vector. So in other words, what have we got here? That z plus w we can otherwise write as the following. We can write it as the kind of 1 plus 3, which we're thinking in this additive way is shifting to the right by 3 along the real axis and then shifting along by 1, and then shifting upwards by 2, and then shifting another one up by 1. And that gets us to exactly this point of 4 plus 3i, right? That's how we think of it. That's shifting along by 4 units and upwards by 3 units. So it would seem reasonable that that can now extend to a general definition. So let's see if we can do that. We can say now, given any two complex numbers, and we write them in the following way of a plus bi and c plus di, and they're both complex numbers, we define the complex addition of z and w as a plus c plus b plus d all times by I. And that's exactly consistent with what we've got here. In other words, we kind of extended this idea of additive actions on the real number line and the imaginary axis as well, on the real axis and the imaginary axis, to the whole plane. So whatever the transformation properties were of the real numbers and whatever the transformation property of the imaginary numbers was, that it now extends in a way to every single complex number. So let's see this kind of for a couple of examples. So if we fade everything away here now, and we just continue with our kind of, we just got our red dot here representing still the complex number 1 plus 2i, how would that act now on the complex plane in an additive way? So how would it act on all points in an additive way? Well, it would just shift all the points along 1 unit to the right and 2 units upwards. So we can see that here, that it takes the entire plane and shifts all the points like so. In other words, here we can see exactly what we just saw a minute ago, that the origin, the point 0, gets transformed to exactly where the point z is, and all the other points get shifted along by 1 unit to the right and 2 units upwards. So we can kind of just do this for a couple more examples, just so we get an idea here of what our definition of complex addition is constructing. So here we've now got the complex number minus 4 minus 2i. How would that act on the entire complex plane in an additive way? How would this number transform the entire complex plane in an additive way? It would just do it in the following way. We just shift down our kind of origin, so our origin now lies at exactly where that point is. And just to see a final one, but hopefully you get the idea, if we take this point here, which is minus 3 plus 2i, and we say how does that number transform the entire complex plane now, it shifts everything along by 3 units to the left and 2 units upwards. In other words, it transforms the plane like so. So we've extended this idea now, where we started off, let's say, way back in some of the earlier videos about how the real numbers act on themselves via addition by shifting left and right. We then understood the imaginary numbers to act on the real numbers by shifting them up and down. And now we've constructed this idea of how complex numbers act on the complex plane by doing a combination of shifting right and left and up and down, which makes sense. So in other words, if we think of complex numbers in this additive way, all they're representing is just shifting things left and right and shifting things up and down. They just represent kind of shifting transformations in the two-dimensional plane, which is not particularly imaginary and not particularly complex. It's quite a kind of obvious idea when just thinking about geometry. And we'll see in a kind of future video how we can kind of extend our idea of complex, or at least our multiplication of the imaginary unit on the imaginary numbers and the real numbers by rotating by 90 degrees. We then want to ask ourselves the question, how can we extend that to the entire complex plane? How can two complex numbers, or if I take any complex number and act it on another complex number in a multiplicative way, how would that transform the plane, and see if we can extend that? So that's where we're going to conclude the video. And next week we're going to explore, as I say, more about this idea of complex multiplication extended over to the entire complex plane and see how that works, as well as introduce some other ideas about complex roots, roots of unity, and various other kind of interest topics about complex numbers. So I remind you to read the notes as well after watching the video, or if not before, as well as attempt any of the questions in the module handbook pertaining to the topics discussed in this video. So thanks very much for watching, and see you in the next video.